Quick show of hands. How many people recognize the song that was playing? My favorite song is called Bella Napoli. It has been added to the CS153 Spotify playlist. For anybody who has music requests for CS153 this quarter, also known as AI Coachella, we've got an open playlist. Please feel free to add songs there. That one was a request from me in honor of our speaker today, who I'm very lucky to call a close friend and is the co-founder of Black Forest Labs, Andreas Blattmann. Thank you for joining us, Andy.
Thanks, Anj. Thanks, everyone. Thanks for having me.
Andy is joining us from Germany in a little town called Freiburg, which I think a lot of you will be hearing about more and more as it becomes a hub for frontier research in Europe. If you remember, in our first lecture, right, we talked about the anatomy of frontier AI progress. And we talked about 3 or 4 important touch points in this class you're going to be hearing about over and over again. One is that there's a transition happening from the old systems, the old infra stack, to a new one, right? And you got to be open to understanding what those rewrites are looking like. And our speakers are going to tell you which parts of the stack they're helping to rewrite. We talked about the basic AI scaling recipe, right? We've got 2 sort of loops that are important to run. Once you do, you get some compute, you get some data, you build a model, and then you do inference, right? That gives you revenue to buy more compute and then context feedback. We've talked about the bottlenecks, right? On getting those loops scaling, which is context, compute, capital, and culture. We talked about context and compute. We'll talk a little bit about all 4 today. And then the last was, well, for your projects, which is the part I'm sure many of you are anxious about, is how do you get one of those scaling flywheels going, right? And we talked about there being sort of 3 steps in the journey. There's an incubation phase where you kind of figure out which specific part of the frontier you want to attack with a state-of-the-art system, right? Then you land with a SOTA release, a state-of-the-art release, and then that allows you to expand to more and more capabilities on the frontier that you care about. And if you remember, we did sort of a field trip into one of the frontier factories, right? In our first lecture, which was Anthropic. We talked about code as one domain. And today, we have a chance to do a field trip into another frontier AI factory in Germany called Black Forest Labs. And we've got here one of the factory owners, Andy Blattmann, who's the co-founder of Black Forest Labs, also co-creator of Stable Diffusion. How many people here have heard of Stable Diffusion? All of you. Perfect. Great. So you've done some homework. And so today we're going to talk about the frontier. On Tuesday, we talked about the audio and the speech frontier, right? What is audio intelligence like? What was it? Where's it going with Maddie from 11 Labs? And today we have Andy talking to us about the frontier of visual intelligence, which I think is one of the most exciting frontier, if not the most critical frontier to unlock more progress. And if we really want to get these models to work in mission critical contexts in the real world. And so we're going to spend some time talking about the anatomy of visual intelligence as Andy sees it as one of the pioneers of the field. And then we're going to go back in time a little bit and zoom into how we bootstrapped the Flux flywheel together a couple of years ago. Flux is the name of the flagship model family from Black Forest Labs. And then we're going to spend some time on the fun part, which is future frontiers. Where are things right now where are there unsolved problems? Where are we right now where you guys can step in and start co-creating this journey in the space? So this was the frontier factory, right? We talked about this is sort of the basic template. Again, to be clear, this is a directional heuristic. Every team is different. Every research project is different. But to kind of give you a grounding sense of repeating patterns about how some of the best teams are manufacturing intelligence repeatedly. Remember, this was the pipeline. We had pre-training, mid-training, post-training with agents in the real world. There's a version of this that Andy's going to walk us through. But before we jump into that, why don't we just spend some time on you, Andy? Who are you and how'd you get here?
Yeah, cool. Thank you, Anj. Thanks again for having me, everyone. I'm Andy. Started looking into AI, I think in 2019. I was actually originally studying mechanical engineering. It's classic German education, I think. You go to school and then you figure out you're kind of somewhat technical. And what are you doing if you don't know exactly what to do? Studying mechanical engineering in Germany, right? And then through a couple of, I think, coincidences, I got into computer science, into coding, into already robotics back in the days. We talk more about robotics later. And applied at a PhD in Heidelberg, where I met my two co-founders, Robin and Patrick. And that was a really like small lab. Everyone back in the day was doing representation learning with visual models, or like for the visual domain. And computer vision in itself that was 2019, was kind of a niche topic in this niche topic back then of AI. It was really like people saw the potential already, but no one had an idea of how that would explode then later, right? So it was really kind of a niche topic we worked on, but we soon had a very good intuition about like how to train models to generate pixels, mainly images back then. And we're competing on a research level as a very small lab with players that were much larger than us. And finally, that already back in the day was Google and OpenAI, their research teams, and it was not about building frontier systems. It was
Foundation models.
Yeah, or even before that, who wrote actually the nicest paper to show that something was happening.
Right.
So back in the days, it was like,
this was pre.
that was pre-Stable Diffusion. That was
20.
Really, it was
19.
For the ones who remember it, StyleGAN was
StyleGAN.
Kind of,
yep.
The images were most often generated with GANs because they had a kind of a good inductive biases for kind of this data domain. And it was generating a 256 by 256 pixels image. Was a challenge. Like not every algorithm could do that, and it was just a very different world. So we competed with labs that were much larger than us, and we had even back in the day way less compute. So we had to come up with kind of more efficient algorithms to solve that problem, because images, and not speaking of videos, are so much higher dimensional than other representations, say text or something. Text is much lower dimensional.
And to anchor folks on time, this was when you were at the University of Heidelberg.
Exactly.
Right.
Exactly. Yeah. And then we spent like 2 years investigating how can we actually find representations for natural data, for images, for video, mainly, that are perceptually equivalent to the pixel space, or to what matters to us humans in the pixel space, but much lower dimensional and much more efficient, because we didn't have the compute to train a kind of generative model on the pixel space. And it's also super wasteful. And that was what gave rise to a series of papers on latent generative modeling. So you actually train a kind of a compression model, similar to a learned JPEG codec, you could imagine it, to find that perceptually equivalent representation to the pixel space, and you train the generative model there. And that helped us saving tons of compute, training our models much more efficiently, and with orders of magnitude less compute than our competitors, put out like better, like models that were on par or even better than those competitors. And that was what that algorithm, latent diffusion, also gave rise to Stable Diffusion then. So we proposed the algorithm, saw the potential, set out to search some compute, luckily find that in the open source community, and trained Stable Diffusion that was then released in 2022, and pretty much surprised us as well, like with all the hype it got. And actually it was fun. It was here in the Bay Area, it was hyped much more than in Germany. In Germany, still today, not a lot of people know about that model, funnily.
Yeah, there was a moment, I remember, DALL-E 2 was in preview, I think. And then you guys put out Stable Diffusion. And I remember on Reddit, somebody had sketched out, they'd taken one of their kids' like drawings. It was like a crayon drawing, and had run it through the image to image transfer on SD. I think this was SD1. And out had come this beautiful illustration. And I remember taking a screenshot of that because I was just blown away, and I tweeted it. And I think it was like a Monday morning. We went into our exec meeting at Discord, and then I came out for lunch, and the tweet had like 3,000 or 4,000 likes. And it was like for me, it was a moment where I realized that the technology of generative modeling at that point had crossed an inflection point where it suddenly became legible to people outside the machine learning community because it was so visual.
Yeah.
Right. I think it might be worth spending a couple minutes here to just take people back in time, because at this moment in time in the ML community, I would say there was a bit of a dogma that language modeling was the be-all and end-all of intelligence. The general consensus at the time was that language is the interface to reasoning, for intelligence, which are the way humans reason about intelligence, the way we think is through language. And I would say that's a philosophical belief that has come and gone in its sort of the strength of its religious zeal. But for those who are in the computer vision community, and I count myself as one of those because my last company, as we've talked about, was Ubiquity 6. It was a 3D mapping and computer vision company. We were working on 3D reconstruction. It was clear that language was extraordinarily valuable, don't get me wrong, at reasoning about certain tasks and fields. But for those of us who are in the computer vision community, it felt incomplete because language is just one way we communicate, one way we reason about the world. For those of you who are visual thinkers or visual intelligence, who believe in multiple intelligences, right? You just learn better when you see visual representations of things. And so it was quite cool to see Stable Diffusion coming out and make progress of a different kind legible to both the machine learning community as well as the broader developer community, the broader consumer community. And that's when I think we reached, we started working together because we were trying to get some of these Stable Diffusion like capabilities onto Discord. But can you talk about it? You said two things that I think are quite helpful to overlay for the students here, which is the difference between natural and unnatural representations. Yeah. Could you speak about that for a sec?
If we think about ourselves, if everyone, you look at me currently, hopefully, and the medium through which you are perceiving this is clearly video and audio, right? You hear what I'm saying, and you're seeing me gesturing here or talking to Anj. So these are what I call natural representations. If you think about the source of those representations, eventually it's the sun. Or here we have some lights that try to resemble what the sun does, but it's electromagnetic waves of a source that we humans cannot control. We can shape obviously we can control the shape of this world and we can build buildings, but the electromagnetic spectrum that falls onto the earth we cannot control. Same for sound, like natural signals, like hearing a river flow or something. That's just some might call it noise or something. That's just natural and it's there. Whereas text is inherently human made. You see this in so many different occasions. If you just measure the information per sign that text transports, it's so much higher than the information per sign per pixel in an image. And why is that? Because it's human made. It was evolutionarily very important for us to communicate efficiently. And I think that's also at the heart of why we need to compress images and videos before we train a generative model on them, because there's so much redundancy in it. In text, you don't have this redundancy because it's human made. Right. Throughout evolution, we reduced that redundancy and made it efficient. For learning, however, it's super important, at least in how I see it and how we see it at Black Forest Labs, to consider two things. First, if you think about yourself as babies, how you learn, it's first observing things, hearing and seeing, and then interacting with things in the physical world, right? This is pretty much the first, I would say, 3, 4, 5 years. I don't know when I learned reading, but it's, I think maybe with 5 or something. And just the level of intelligence a 3-year-old has compared to the level of intelligence a language model has is very different, right? And I think that's why we care so much about natural representations like audio and video, because we are like absolutely convinced that this will be the fundament of all the kind of higher intelligence that these systems will eventually have. And starting from language and trying to stack up a bit of additional kind of representations on top of that is, in my kind of opinion, the wrong way. You should start from first principles, how we humans do it, and that's clearly learning on natural representations by first observing, and second, we'll talk about that later, interacting. These are, just from how we think about it, the main pillars of learning and also the main pillars of what we define as visual intelligence, actually.
So I think this is pretty important because 2 years ago, 3 years ago, I would say the consensus was that the way to do generative modeling was roughly this, right? Where you had these foundation models that were unimodal. They were text to image, text to video.
Looking at
right?
Stable Diffusion, yes.
Stable Diffusion was
text to
one.
image model,
Yes.
exactly. Unimodal based on images.
Yeah, but could you just talk about what the state of the art was then versus now?
Yeah. So Stable Diffusion, I think it's a perfect example of that. It was a text to image model. You could do super nice kind of artistic things that have not been possible before, but it was clearly made for content creation, right? It was a unimodal model made for the purpose of content creation. You could make artistic style transfer. You could train a LoRa and do maybe some kind of character consistent marketing transformation, or character consistency into the get character consistency into the model, then use it for marketing or something. But that's all content creation. We currently see that visual models starting to become way more than that. We don't train a single unimodal model anymore to just fulfill the purpose of content creation. We're training a unified, a multimodal model for natural representations or natural data that then can give rise to so much more. It's about physical AI. It's about robotics, computer use. We can do with these models. We had a couple of demos already, or there were recently a couple of demos that were super impressive. We can do world modeling and simulation and still content creation. But combining different natural representations, not only training on one, is the key ingredient, because it will give the model a much more natural understanding. As one example, if I just see two rigid bodies colliding, I always have a sound attached to it, right? There's a correlation between that sound happening and a certain action in the physical world happening. And being able to observe this correlation for a model is super important, because it will help that model understand much better what's actually going on. Whereas if I only train at one single modality, it's much harder to kind of understand what's going on, or just interacting with this model. I think it's super hard for a model to understand what's actually going on if it doesn't hear that sound. How would that be different for that kind of transparent body compared to someone putting their hand through water or something, which is also transparent, right?
Right.
So these correlations between different natural data representations are super important for a model to learn kind of at a higher representation of intelligence as well.
Now, this idea, for those in the machine learning community, is not new. I mean, for a while there was a sense that the progression of technology would be, we'd have sort of state-of-the-art systems that were capable at individual modalities, and then at some point, to make them smarter, we'd have to give them the ability to reason across different domains, transfer learning, so to speak, where you can reason about the physics of this bottle hitting that, and the sound, the audio emerging. But you can't start with everything on day one. And so could you just let's talk about how we bootstrapped the flywheel. Because now today, fast forward 2 years ago, 4 years after Stable Diffusion came out, Flux is now used by millions of people around the world. You guys have hundreds of millions in revenue, blah, blah, blah. But for the purpose of the students, I think it's helpful to zoom back in time and say, okay, you guys had this clear thesis for eventually models will be good enough at reasoning about all of visual intelligence. But you have to start somewhere.
Yes.
Especially when you have less resources than the largest companies in the world. You're a smaller team. You have less data. So can we spend a little bit of time talking about how did you concretize where to start?
Yeah.
And then how did you initialize that kind of momentum flywheel we talked about at day one?
Yeah, absolutely. Yeah, I think that's one of the most important things when starting a company. Focus matters.
Well, or any research project, right? At the time, actually, SD was not even a company.
Absolutely. But I think I want to, as an example, I want to take how we started the company, because there we had this kind of huge experience in image generation, unimodal image generation. We've done Stable Diffusion, then we've worked for Stability AI, put out a couple of more models on that domain, and we pretty much had the recipe to kind of train a frontier model for that domain.
Right.
So when we started the company, we looked at the field and we said, there's clearly a need for a next generation of image models, because so far the models cannot, say, produce hands that are actually having 5 fingers, right? That was back in the day a thing. So we attacked that specific field and said, okay, we want to be building a model for specifically for image that is just 10x better than everything else. And then we sat down together 3 months. We had all the recipes. We knew what to do. We scaled it. And what came out of that was Flux 1.
Right.
That initially had kind of product market fit, you could say. We even before we took our API public, we had a couple of very large customers that kind of helped us close the feedback loop. Now talking about the feedback loop, because obviously once you can build a technology, but setting that technology out to solve real world problems will give you the very important kind of data to actually learn from, first, what is an important problem to work on, and also how to make the model better for that specific problem, right?
Yeah.
By that you have the first kind of loop closure for the flywheel.
I mean, let's break that release down. Flux 1, I think this is the kind of pipeline we talked about, right? So could you just go through sort of the BFL version of this and explain what's going on at each step within the company of the BFL sort of pipeline?
Yeah. So I mean, this is particularly for how we would define visual intelligence now, but I think I can also for Flux 1, it was clearly we trained only on unimodal, like text and image, right? Only on those representations. So the pre-training was just a large corpus of text and image. For the mid-training, we added higher resolution and like a couple of more capabilities into, and then we had this kind of post-training phase where we exposed the model to. First, we did a kind of offline post-training before you release an initial model. Do some distillation to make the model more efficient. You align it with your intuition about what customers would care about,
right?
And then you expose it to kind of the real world. But then you get this feedback. And for Flux 1, a very interesting observation we made was, oh wow, so many people are using our text-to-image models to actually train a LoRa and then do character consistency. Like they want to have the ability to control the model with more than only text, because text is obviously nice and easy and low key. Everyone understands it, everyone can use it, but it's also very ambiguous. If you like, and again, there's a kind of disconnect between this kind of artificial representation text and the natural representation image. So if I say an image of a blue bird, there are infinitely many images that give rise to this kind of description, right? The bird could be sitting on a branch, the bird could be flying, and so on and so forth. And it's actually super hard to apply precise control to image to the image you want to be generating. So that was I think that's a perfect example of the benefit of the loop closure, because what we learned was, okay, people want to actually do image editing.
Right.
So what did we do? We did a post-train on partially based on the data we got, partially based on new stuff, to create an image editing model, which was Flux 1 Context, that came out, I think, pretty exactly a year, bit less than a year ago. And that was the first image editing model where you could actually, in a scalable and fast way, get character consistency. So now I could take an image of you, Anj, and say, and maybe of me, and combine us two sitting together on a lecture hall, but in a cafe having a chat. And that just has massive potential for everything content creation, right? Marketing needs it to like get different products into different contexts, and it's just like supercharged, or currently supercharging, like a lot of different applications around the creative world.
Yeah, so this may not be obvious, but I want to pause here because Andy did this quite naturally. But for those of you who were trying out AI image models, let's say 18 months ago, how many of you tried giving it a photo of yourself and then saying, give this person a hat, and then it came out actually looking like you? Yeah, no hands are going up. One hand is going up. It was a pretty basic capability gap. These image models just didn't have character consistency, right? You just give it like a photo of yourself and say, give him a mustache or whatever, and out would come somebody looking not like me. And that for many people in the space, that was just I actually can't. If I had $1 for every time, people would say, that's just, that problem will not get solved. Like, these models are so dumb. Like, look, AI is so dumb. It will never, like, it'll never be able to surpass that capability threshold. I would just sit there, and these are very smart people, including, by the way, some of the speakers in this class, who over the years have realized they had to update their priors about the speed at which you can update these capabilities. But it was common consensus at the time that these image models are just not going to get that good. AI is dumb. It can't reason about the way that humans do about faces and specific characters. And I was shocking to me how very smart people would very confidently proclaim in the industry that I was just not going to get solved. Meanwhile, here we were in Freiburg, looking at the data, where there were people using Flux, which was not very good at character consistency, but that context feedback of seeing how the prompts people were trying to use with the model, and the feedback of them saying, actually, that was not good. Can you please try, doing this better? The multi-step sort of reasoning chain that we were getting from seeing people out in the wild using it. It was an open weight model, which we'll talk about in a second, which is quite unique. Gave us a very clear path actually to improving the capabilities. And then actually it was, one of our team members, Dustin, in SF, who figured out that, we should just make an update to this that's called context with a K, because that's the German way to pronounce it, that is specifically an editing model. And I think between that insight, which was at an offsite in Spain, where were we? We were in.
I think it was in Italy.
In Italy, we were in Italy. I think GPT-1 image had just come out. Yeah. We were literally all together, and there was a sense, this is an important thing as a new team or as a first time, researcher. It can be quite daunting when some lab that has way more resources than you launches something that looks way better. And your first intuition is to go, oh my God, we're But you got to remember that the mark of a good leader is to not panic, keep calm, look at the data, assess the landscape, and then come up with a plan step by step. And often you'll notice that if you're good at mapping the domain you want to be an expert in, somewhere in your intuition, you have a gut feeling that's telling you there's actually some unsolved problems still left. And Dustin did a great job at that. The team rallied. I think within 24 hours we had redone the staffing on the team, and I think 60 days later, Context came out, right? And revenue from Context doubled, I think, within 6 weeks. In fact, I think soon after is when this part is public now, that Meta announced a partnership with BFL and said they were going to be using Black Forest models. This tiny team out of Germany, I think the team was, you guys were like 25 people?
Yeah.
To drive image editing for all 2 billion Facebook and Meta and so on users. I mean, this is not normal, right? And observing, I was lucky enough by this time, I had been an investor with you guys for about a year and a half. And so we would go to these offsites together, and I had a chance to sort of see how in real time, this is the systems problem often is not just a technical problem, because actually all the data was available to us, the context was available to us. It's the human system of organizing the team and the research sort of culture, right? In a way that is not, you're not panicking, but you're still assessing kind of the frontier methodically, and being very honest with yourself about how fast capabilities are moving and where you can uniquely sort of contribute to that system is the key to keeping that loop going over and over and over again. And I think that's why, BFL is where they are today. They went from 0 to several hundred million revenue. The company is now worth more than 3 billion. But it can be easy to forget that wasn't always the case. And there are these moments in your journey, especially in machine learning, where things change so fast, that it's very tempting to just give up. And say, you know what, this problem is solved. I mean, it is remarkable to me how many teams in image generation just no longer exist because they just gave up. And instead, BFL just stayed persistent, and today is one of the only leaders left. I would say an independent leader that's pushing the visual frontier. In fact, I hope some of the projects here push the frontier too. But that's I think a learning for me has been, it's actually quite straightforward sometimes technically if you have the right leadership to keep advancing the frontier. But sort of a drift in your mission, a lack of conviction that, it's worth attacking the problem you're committed to over and over again in the face of crazy challenges is often just the difference between, success and failure. How many people have seen that meme of the guy tunneling and giving up right before? Yeah, you guys know that meme. We'll put it in the class reading list. I'm dating myself with boomer memes here. But I can't tell you how many times it's felt like that at BFL, and then one release later, right, the world has changed.
And that's actually, I think, also a good segue into what's next. Like now we're seeing this kind of these models being applied everywhere for content creation. But again, then you need to think more, or like look forward and think, okay, what's next? And clearly, we now see this insane potential of especially these combined multimodal video, audio, image models for the capabilities we just talked about, right? Physical AI, computer use,
right?
World modeling and simulation, and still also content creation. And you can actually build a single model that is capable of doing all of that together, and you will actually get compounding effects based on this example with the correlation of noise and action in the physical space. You can also make models that are much smarter for generating regular images or video footage for, say, again, advertising or something.
Well, could you talk a little bit about that? So let's zoom forward to, actually, could you talk about, how do you take an image or a content creation pipeline and add to it what you just talked about, the ability to actually interact with the physical world or learn from the physical world? What does action prediction mean? How is that done? And then maybe you can talk about self-flow a little bit, since we're going to be assigning that as reading.
Yeah, absolutely. So I think first you need to go from, we already talked about this, unimodal to multimodal.
Right.
And then you get this kind of, this is this one. And if you go back to the slide here, I think this is a good one. So there's a large pre-training on, again, natural representations. These are the representations we humans use to learn from in our first years of our lives. And there you just combine everything together, and you have these this combined pre-training that gives you a very, very general model. So pre-training for us means images, video, audio, combining with an architecture or with an algorithm that we've also published beginning of March, self-flow, which allows the model to actually get compounding effects by observing. Again, I don't make this example again. You saw it already a couple of times, by observing correlations that exist between those modalities. That gives you a very, very general representation. What we add next in mid-training is additional context. We do new tasks such as conditioning on. I can condition a model on an input image and an audio track, and I say I wanna hear Anj saying XYZ in that voice. Model does this. This is additional context, but importantly, for extending the scope beyond pure content creation, you also want to condition the model on actions, and you want to have the model predict actions. And then we can arrive at models like this computer use models, for instance, that are conditioned on a video or an image, and they predict the next move based on keystrokes or something to achieve a certain task. Say I want to be opening a new browser tab or something, right? So this is crucial to expand the scope of this kind of very general representation that we get from pre-training, but we actually want to be using it we want to make use of this kind of generality of the representation. So we add additional context and, importantly, actions. And what we then do, this is very important, or maybe to zoom out a bit more and come back to the human learning example. Pre-training, mid-training, this is all still observation. All the algorithms that we're training, like foundation models with in the early training stages currently, are models observing examples. We're calculating a loss from that. We back propagate that through the network, but there's no interaction whatsoever.
Right.
So how do we actually get the model to interact really in the physical world? That's super important for kind of learning higher forms of intelligence, as we are all convinced of. So what do? We use this model that can actually, given a video, predict an action to do something and hook it up in the real world on a robot, for instance, right? And then that allows us to allows this model to, through a robot, interact with the physical world, create data for that again, and we can pipe that back into the model training. And that's when we close this feedback loop. So our post-training means interacting with the physical world.
Right. So this is important. If you guys remember, we talked about physical verification, right, as a key predictor where frontier progress is going to continue. Wherever you have context that can be, and performance that can be verified, progress can quite reliably be made there, right? So in software engineering, that's verifiable because you can write unit tests. In image generation, not very verifiable, right? Because beyond the basic tasks that Andy talked about, which is accuracy, right? 5 fingers instead of 6, character consistency, which is more a preference.
But even that example, how would you measure that at scale without having a human telling you?
No, exactly.
This thing had actually five fingers.
Well, I think you should talk about how that verification works, and then what is the, in the new world where you have to verify physical tasks like robotics, what does that look like?
Yeah. So I think it's fun because so verification for images is super tricky, especially when it comes to or for videos when it comes to physical things. But once you hook that up in the real world, there are just certain things that you can do and certain things that you can't do because a robot arm cannot just do certain joints. So it's like exposing it to the physical world naturally applies the boundary conditions that we would expect. So that's a very important step, and by that you have the perfect kind of environment,
right,
to directly inherently model these kind of restrictions.
Whereas in the case of aesthetics or visual preference, how did you guys verify that? How did you get a model to be better when just doing content creation?
Yeah.
That
involves like massive amount of human judgment and then feedbacking that signal through the model again.
Right.
But that's like often very tedious and also often very dependent on who you're asking.
Yes.
Like if I ask you, you've looked at so many images by now. I would consider you an expert because we always show that guy our models, but you're also enjoying it, I guess.
Depends on how much spits you have had that and my energy.
But like showing an image to someone who has no idea of say image generation versus to myself, and I've looked at so many images, it gives you a very different signal. I would rate something as good or bad that looks very different from what a kind of another person would do, right? It depends on the crowd who you're asking. So you can ask people, right. That is very very ambiguous in a way.
So this is a key insight, I would say, because anytime the answer to the eval question of how do you verify is it depends on the audience or it depends on the person consuming the system, it should trigger a light bulb, at least it does for me, that the value that you get from the system varies a lot by how much the model can be customized for a particular audience. And that is where open source comes in. Because the beauty of open models is if you give away the weights, and they're good general weights, right? Then you can tell Meta, hey, you're welcome to customize the preferences of this model as you see fit for your users. And you can tell another government that has different cultural preferences and biases that wants to, be able to deploy content creation for, let's say, internal teams in a completely different culture, and say, you can have the control over that last mile. And I think that's turned out to be a very critical part of the open ecosystem, where I often get asked on, why did BFL open their models up and just give away all this research for free? Is it just that they want to save the world? Well, part of it is cultural. As you can tell, Andy, Andy came from the academic community, enjoyed and benefited from open publishing. But at the end of the day, you've got to turn these research projects into businesses, right? And it turns out there's extraordinary value in producing state-of-the-art systems that are then open and customizable when the consumer of the system, the person benefiting from the system, has very different preferences from other people who might be consuming the system. Does that make sense? Have I lost you guys? Can I get some nodding if that's making sense? Yes. Okay. This will be a theme consistently, okay, in the class, which is anywhere you have consumers of a system or customers or the people benefiting from the system wanting more and more personalization and customization of the system for themselves, that's where open models become extraordinarily valuable. And you can actually build, it turns out, a very large business very quickly doing that. So I actually think there's a false trade-off in the space a little bit about open versus closed. These are both just techniques or tactics for how to deliver value. Sometimes they get politicized philosophically, but actually just from a very basic first principles commercial perspective, open makes a lot of sense in some domains where the aesthetics, the preferences, and so on are quite. There's a long tail of the distribution is quite wide and heterogeneous, versus domains where preferences are actually quite narrow. If there's a pretty narrow distribution, then I think closed models and so on are quite valuable in that case. I think there's one last piece that we haven't covered, which is the state of the art today. Because as Andy said, now the state of the art, right, is about how do you get these systems to reason in a unified fashion across text, image, video, and so on, in a way that has transfer learning across these different modalities. A very hard problem. Very, very hard problem. But as is the case with BFL consistently, the team has, makes these sort of research advancements and then gives away the technology. And so this was actually one example, I think, 2 months ago? No, a month ago. Self-flow, which has turned out to be a technique. Now that suddenly, magically, all my friends at all the labs are calling and saying, Anj, have you heard of self-flow? I was like, yes, we have heard of self-flow. It's on archive. Because Andy and team published it. So maybe you can talk a little bit about what the intuition behind self-flow is as a mechanism to solve the multimodal reasoning problem.
So when training visual generative models, it's always been historically a bit tricky to get representations into the model where they don't only generate pixels in a way,
right,
but also understand what's actually semantically going on. And there has been a body of work on that worked on aligning representations of generative models with representation learning representations. That
getting meta there, yeah.
to get them a bit more understanding of what's actually going on, and not only make them stupid pixel generators that just learn to kind of resemble what looks consistent in an image. That has been, in the last 2 years, always been focused on single modality. So what people did, they used a pre-trained representation learning model, like maybe some of you might know the Dino model for images, pre-trained model, and they tried to just make the representations that the transformer, that is a backbone for image generation, has internally aligned with the representation that this representation learning model had. And that is clearly restricted once you want to go multimodal. But as you saw in the last slides, going multimodal is super important to learn kind of higher form of intelligence. We want to be we want to have models learning multimodal representations because that's frankly what we humans have, right? So it's crucially needed. So how can we actually combine learning, having these so-called alignment losses with multimodal representations? And the self-flow paper solves exactly that problem in a very natural way. Really recommended read for everyone. It's
assigned reading.
Super nice. Yes.
Okay, good. Shall we transition to questions? Okay.
Yeah. So the question was, when we close the feedback loop, how do we ensure to compress this? How do we make sure that actually personal data is respected and that no harm is generated based on those models? So first, we have a lot of content filters on our API, obviously, because our belief is that these models are powerful tools for humans to create super nice and creative outputs, and also much more than only content creation, as we just saw. And we don't want to have them misused, so we add a lot of content filters that actually make sure no harm is generated. On the personal information, obviously being based in the European Union, we comply with the EU AI Act, and there's actually a kind of law that we also follow, that you, based on a request. So if you put in an image of yourself on our API, and you say, hey, look, I don't want you to store this kind of data, we have to delete it. So we have systems in place to actually make sure this basically happens. So the question is, like, we had a lot of partners, large companies that we worked with, like XAI, Meta, backed by Nvidia, and the question was, how do we evaluate with whom we work and with whom not? I think maybe as a general statement, we're working on building visual intelligence infrastructure for everyone, basically. So from an infrastructure perspective, you really want to make sure you put guardrails around your models, that people cannot misuse those. But then infrastructure is there for basically everyone, right? And that's the standpoint we're also taking. We care a lot about the safety of the models. That's important. And we do everything we can to prevent misuse. But then I think it's also us putting out the technology there and providing it to everyone. And it's always hard to take a certain standpoint on like who you're working with, who you're not working with, because it gets very tricky to justify in the end.
Let me try and translate what Andy's saying. The company basically applies its guardrails to everybody. So no matter who you are and how big you are and how much money you've got, if you want us to remove our guardrails, sorry. Those guardrails apply to everybody equally, because being a standard and being infrastructure that people can rely on means you don't treat different people differently. And everyone can rely that they're not getting, just because they might have more money or they might be more politically influential, whatever it might be, that they can get the same quality of service as everybody else. And so that's the position BFL's taken as an infrastructure provider, is that doesn't matter who you are. Now, sometimes you have custom needs because you have of the scale that are technical. Hey, we need it to be deployed in this way. We need some latency requirements that are more technical. But when it comes to guardrails, that applies to everybody. And so when some partners say, we want you to remove those guardrails, say, sorry, you can go elsewhere. And that has resulted in sometimes the company losing meaningful amounts of revenue. And that's okay. Because in the long term, as we talked about in the first lecture, the way you get infrastructure to move stably is you have trusted standards and trusted institutions to enforce them. And sometimes you got to enforce them yourselves. Would you say that's roughly correct?
Thanks, sir. Yes.
We've had some spirited debates, I would say, at the company. And, we've talked about culture as a bottleneck on progress. One of the secret sauces of BFL is a very united culture where there's a lot of debate and dissent on what to do and not to do. But then when they commit, they all commit together. I mean, how many people have left the company in the entire lifetime of the company? Like 2?
1.
One. They've had one person leave in the entire history of the company. Not common in the AI space, where sometimes you have like co-founders leaving 6 months in. I'm sure this is the thing. This is my one issue with the Bay Area. The culture's forgotten that sometimes to make progress on long-term ambitious goals, you got to stay together as a unit. And that's a great question. I think it challenged, I think the culture at several points, and I think they turned into sort of moats in a sense.
Yeah, absolutely. You debate, then you disagree, and then you commit.
You commit,
and onwards then.
And there'll be more, I'm sure. Next question, yes.
The question is, how do we deal with the insane amount of data labeling that has to be done? And other than for text, images are just like not that straightforward to label. I think 2 answers. First, when we train a model, we start obviously we just saw this kind of pre-training, mid-training, post-training stages. We start with more data and also more noisy data in pre-training. And then as you progress through training, you reduce the amount of data, but you increase the quality. So for in pre-training, it's enough to do automatic like labeling that you can automate and then really apply it at massive scales. There are systems that are available to do this, also publicly some, but obviously also we have some internal stuff that I can't talk too much about now. But then the more we approach later stages in training, the more we also involve, say, human signals and stuff like that, because you want to make sure, as you say, that in the latest stages of training, where you actually then again align this kind of very broad and general representation your model learns with what actually matters most to everyone out there, you want to make sure that this is actually, you have annotations that reflect exactly what you want. And that's when still the gold standard is involving human labeling then. Where do we see the field going in terms of denoising, just in general, iterative denoising? Will it still be needed in the future? There are now other probabilistic approaches such as drifting models that allow us to do maybe a single step. And yeah, I'll answer that very generally. I think it's super interesting if you compare these kind of flow matching diffusion models with language models. Both are iterative models. But flow matching models or diffusion models are iterative in a dimension that is orthogonal to the data, in this kind of time dimension artificial time dimension that we apply, that goes from pure noise to kind of the data you want to be generating. Whereas language models are iterative in the direction of the data, right? You generate token by token. And that has very interesting implications for both the training and the inference kind of properties these models have. For diffusion flow matching type models, you're actually pretty data inefficient, because every training example gives rise to infinitely many kind of potential losses, because you can pick every kind of point on the continuous trajectory from clean image to noise and say, I want to denoise from here to say the next step, right? And then I can do this super often. So that tells us it's super data inefficient in a way compared to language models, where we can train on all tokens in parallel, or let me specify language models a bit more autoregressive models, where we can train on all tokens in parallel. On the other side, we have at inference, it's like these two properties being switched. So, or the effects of these two properties being switched. When you see language models, you have to generate token by token, and there are some hacks such as speculative decoding and stuff like that that maybe can help you. But essentially, you still have to, you cannot just miss data. Whereas for diffusion models or flow matching models, you can actually distill a model down, right? What we do when we do post-training, we do distillation. We've written a bunch of papers on adversarial diffusion distillation, where you get down the kind of number of steps from flow matching models from 50, say, to 4 or 2. And then it actually doesn't make a real difference anymore if you then do a drifting model and you have this then directly at one step maybe, or you maybe take 2 steps, but the pipeline is just more stable and mature. When you distill a diffusion model down to 2 steps using adversarial diffusion distillation, right? So I think it's two things of the same, of the same side of the coin. But coming back to autoregressive models, that's not really like possible for getting these insane speed ups by just distillation in the or using the iterative nature of the model. That's not possible. So I think a very interesting research problem that I'm thinking often: how can we combine the data efficiency of autoregressive models with the kind of inference capabilities or inference properties that these kind of diffusion flow matching type models have? So everyone who likes to do research, that's a super interesting problem to work on.
Are you guys hiring?
And
Okay, so
always. And yeah, I could not spend the next half hour talking about this, but
this part is latent adversarial distillation is a very it's a part of the pipeline at BFL that I would say is very near and dear to the core of the company. Not only for 2 reasons. One is because it actually makes these models extraordinarily efficient. And for those of you who have German friends, you know that efficiency is top of mind. And I think that's a through line through everything BFL does. It's high quality, it's efficiency, but it also ended up being a key unlock for our business model. Because early on, a big question was, well, we have this philosophy of we want to be open, we want to produce open weights, but we've got to find a way to make it commercially sustainable. Because there's a lot of projects that open models up and then they just die, and then that's not stable infrastructure either that you can rely on. And so one of the key differences between diffusion models and autoregressive models, as Andy's talking about, is that the model size is actually the same in a diffusion model. If you look at the first Flux family, we didn't release Flux as a single model. It was actually Flux 1 was packaged into 3 different models: Flux Schnell, which is German for fast, right? Flux Dev, and then Flux Pro. And Flux Pro we put behind an API, whereas Flux Schnell was full Apache 2.0 open weights, and then Flux Dev was open weights but a commercial license where you were welcome to look at the weights, use the model, but if you wanted to make revenue off of it, you had to pay. And the key distinction between these 3 was actually they were the same size model. Unlike, for example, language models where you have Flux, like if you have Claude, Haiku, Sonnet, Opus, and so on, they're actually different sizes. So in autoregressive land, you distill down the model, you train a big model, and then you distill down to smaller and smaller sizes. In Flux 1, which is a diffusion model family, it was the same size, but fewer steps.
So you can still do size distillation.
You can still do size distillation, but I think they were all at this point. Public,
for
right?
Flux 1, it was absolutely.
And so we distilled it down to Schnell, which was basically a single step model at that point. So it's
4 steps.
4 steps. Sorry, 4-step model, super fast, super lightweight, lower quality. Pro, more steps, super high quality, slower, right? Because you're iterating over more diffusion steps. And so that turned out to be this very beautiful kind of packaging of the core technology in a way that was also commercially sustainable, because the open source developer community was thrilled, because now they had this really fast model for a lot of use cases that you can run locally. And all the enterprises who didn't want to deal with customization had a high quality model that was behind an API. And developers who wanted the mix, sort of a mix of both, got a pretty high quality model that was also open weights, that was fast. And that trade-off, is a hard one to make if you don't sort of foresee the fact that you want to close this loop that we've talked about of frontier research repeatedly. I'd say 2 years ago, the state of the art was train a model, put it out, put the weights out there, let's see. But when you start thinking long term, then you're not thinking in terms of a single model release. You're trying to think about it as a system. That's capital, we've talked about all the bottlenecks, and you want one iteration to help you unlock the bottleneck for the next run and the next run. And adversarial distillation, latent adversarial distillation turned out to be a pretty key unlock for that part of the bottleneck 2 years ago. Next question.
Spatial intelligence, yes, and whether it's more 3D or like how I see the 3D space where some companies are working versus our kind of more video-based approach going forward in the future. I think I'll take a kind of opinionated view here. Again, it comes back to how do we humans learn in our childhood. I think we don't have explicit 3D representations of anything in our head. We just learn based on video and audio, and I think that's the way that will. Or I don't know if anyone have, at least myself. I cannot look into people's heads, but I don't have an explicit kind of 3D coordinate representation of something in my head. I see you. I have a kind of my eyes are doing a bit of triangulation, obviously, but it's still pretty much a kind of projection onto those 2 eyes. So I think it's I don't have an explicit 3D model of like, say, Anj, this bottle or something else. I just learn it from video, and I can obviously move my head around, or I can interact with this object, and that's all we need. So I'm not a kind of so like I don't believe too much in these explicit 3D representations. It's also a data problem at some point. Do we get all the data kind of labeled with 3D representations? I don't know. Just learning based on natural representations and then interacting with it, as I already said, like before, is in my view the kind of way to go forward.
I'm gonna express a somewhat contrarian opinion to it, and which is actually not totally disagreeing with you, but I would sharpen it to say, I think what we have learned empirically is that these static 3D representations, and I have a strong point of view on this because I started a company that failed at this. Ubiquity 6 was a 3D mapping company. We tried to map the world with reconstructions in 3D using a bunch of deep learning priors. And what we learned was, it actually, don't get me wrong, the technology worked and it was valuable, but explicit 3D representations are very narrow, inflexible, and static. Especially when you take the temporal, the time element out of it, their uses are quite limited and niche. And so there are these applications for 3D representations that are useful, don't get me wrong, especially when you're getting human, like machine perception. Point clouds, for example, are great at having robotics, do indoor positioning in GPS-denied environments. But when it comes to, when you're trying to build a system that can be interacted with by humans, it turns out point clouds, 3D meshes. These are all sort of intermediary representations and, in a sense, hacks to, that are less general and flexible than representations that can integrate naturally time and audio and all these other modalities, because that's how we reason. Now, because I actually disagree with you, Andy. I do think I have a 3D representation in my head of certain things. Like
is it explicit? Are you thinking in terms of coordinates? I don't think so.
Well, I think about this lecture hall.
Yeah.
Like when I'm planning a lecture, I often have a 3D representation spatially, but it's just one input representation as part of a broader set of.
But you're not like there's no kind of prior that enforces you to think about this kind of explicitly.
Yes.
It's implicit.
It's implicit. It's implicit.
You learn it based on like what you're perceiving,
right,
and what you're interacting with.
That's right.
And
that's
and
right.
obviously we could maybe a network could in its weights represent this kind of implicit 3D structure if it needs that. But I think the interface, like we're talking about the interface, right? Do we need these?
Okay, yes. At the human interface level, no, it's quite unnatural to reason in explicit 3D pairs. I would agree with that. Welcome to our late night conversations.
Yes. Yes.
Thank you so much, Andy, for coming.
Thanks for having me. Thanks, everyone.